In section 8.3, we are going to start working with a new irrational number, one of the special numbers used in mathematics. And you'll see that your textbook notes that the history of mathematics is marked by the discovery of special numbers, such as counting numbers, zero, negative numbers, pi, and imaginary numbers. And similar to pi and I, this is the number e. It is also an irrational number. And it was discovered by Leonard Euler, which is why it's called E, after Euler's last name. So what Euler noticed was that as n approaches positive infinity in the previous functions we've been working with, 1 plus 1 divided by n to the nth power approaches this constant e. So what it basically says is that the more frequently you compound interest, the closer and closer you can come to saying that your growth factor can be taken to the nth power, can be replaced with this 2.71828 item. So you'll notice on your calculators that you do have an E key. It's a very commonly used number in financial calculations. And then we've got some exercises in your homework where we actually work with the number E, but at the moment they're really just going to remind you, in essence, that when we're working with a different base like E, it's no different than if we were working with a base that was a number. The rules of exponents haven't changed. So when I'm multiplying powers with the same base, I add the exponents. So this would be e to the negative 3 plus 5, which would be e to the second power. And when we simplify here, 6 divided by 4 becomes 3 halves. And I'll have e to the 3x in the numerator minus e to the first power. So this is e to the 3x minus 1. All right, so it's perfectly fine that I now have a polynomial expression as an exponent. That's fine. To simplify e to the 3x divided by e to the first power, that's what I would do. I would subtract the exponents. Okay, e is a base number that is greater than the number 1. So if you work with e to the x power, you'll have an exponential growth function. Right? Our b value would be greater than 1. If we have e to the negative x power, that would be the same as 1 over e. That would be less than 1, and that would create an exponential decay function. And we would graph them just the same as we already have in previous sections. So if I want to graph y is equal to 4 times e to the x power, you'll notice that in this case, h is equal to 0, k is equal to 0, so I'm not going to have to shift this. When I create my input-output table, I'm going to use the same values I did before. I'm going to use the negative 1 power, 0 power, and 1. Now, this is basically going to become 4 divided by e, right? And e being 2.71, it's almost 2.5. Right? This is going to be, you know, a little bit less than 2. So about 1.5, 1.7, somewhere in there. I'm just going to put that in. For graphing, that will be fine. E to the 0 power is 1 times 4 is 4. E to the first power is 2.7 times 4 would be a little over 10. Right? So we're going to go a little bit over 10. Let's say it's about 10.2. Right? If I go ahead and graph that at negative 1, I'd be at approximately 1.7. At 0, I'd be at 1, 2, 3, 4. At 1, I'd be at 10, a little over 10. And if I graph this, I come in along the x-axis, pass through my 3 points, go out with an exponential growth function. Okay, now you wouldn't approximate these numbers. You have a calculator, you could go ahead and get a little more specific than I have. Right now, in this particular case, it's a little more complicated. I know I have a k value of 4, or negative 4, excuse me, k is equal to negative 4. But this is a little difficult to figure out what h is. So what I'm going to go ahead and do here is I'm going to work with the whole function, and we'll go ahead and we'll do the input-output table. It's a lot easier when you have an ambiguous sort of h than it is and a known k. I'll go ahead and put this down, -1, 0, and 1. I'm going to pick the same items to plug in. Actually, I'm going to put in simpler numbers, numbers that will result in -1, 0, and 1. So I'm going to put in -1/2 and +1/2. Okay. When I put in -1/2 for x, 2 times -1/2 is -1. E to the -1 power is 1 over 2.7. And then we're going to multiply that times 0.1. So this is like a little more than a third, but then I have to move the decimal place a little bit. So this is very close to 0.33. Let's say it's 0.30. If I multiply it by 0.01, I'll do 0.03. 2 times 0 is 0. E to the 0 power is 1 times 1/10 would be 0.1. I forgot to subtract my k, so 0.03 minus 4 is going to be -3.97. And 0.1 minus 4 is going to be -3.9. And over here, 2 times 1/2 is 1. E to the first power is 2.72. When I multiply it times 0.1, it'll be 0.272. And when I subtract 4, I'll get -3.728, something along those lines. So when I go ahead and plot these, at -1/2, I'd be at -3.7 is 1, 2, 3, 4, just a little bit larger than 4. -3.9 is a little higher, right? A little closer to 0. And then at 1/2, I'd be at 3.73, so right about in here. So my graph is going to come in along here, pass through these points, and head on out. In this case, I might have wanted to pick another point out here to be a little more specific. But you can see I can still just pick, again, comfortable input numbers to combine with the 2 so that I could go ahead and graph this. Okay. In our last section, we learned this formula for calculating compound interest. P is the principal, R is the rate, N is how frequently we compound per time unit, and T is the time unit. So if you're talking about years, and let's say you were compounding monthly, N would be 12 in both places, and then T would be the number of years. Using Euler's number, we can actually now calculate for continuously compounded interest. So a compounding N that is equal to infinity, so continuously compounding, and it'll be the principal times Euler's number taken to the RT power. Again, rate will have to be expressed as a decimal. So if we use this in a problem, I know that my amount of money So if we use this in a problem, I know that the amount of money I have will be equal to my principal. I deposited $975 in an account, that's my principal, times Euler's number, because I'm compounded continuously, taken to the RT power. So my rate is 5.5%, that's 0.055 for 6 years, so it'd be 0.055 times 6. That'll be $975 times e to the 0.33 power, which will be equal to $1,356.19. So the key thing you need to look for in any kind of an interest problem is this statement right here. interest compounded continuously. If it says compounded continuously, you're going to switch from the other function, right? We learned this one already. A is equal to principal times 1 plus r over n to the nt power. That's for being compounded in a discrete number of times per year. Compounded continuously would be principal times e to the rt power. Okay, so it's important that you read your problem carefully to make sure you use the correct formula. Right? If we want to look at the difference between compounded interest continuously and compounding interest for a specific period of time, we can take this situation. We're depositing $2,500 in an account that pays 6% annual interest. And let's see what happens when we compound annually, semi-annually, quarterly, monthly, and continuously. For the sake of time, I'm going to do annually, semi-annually, and continuously, but I'll write out the equations for quarterly and monthly, and you guys can do them offline. Right? So first, if I want to calculate annual, I know that it'll be my principal, $2,500, times 1 plus my rate, which is 6%, 0.06, to the t power. And since we're only looking at 1 year, this would be 2,500 times 1.06 to the first power, which is equal to $2,650. If I want to look at semi-annually, now that means we're compounding twice a year. $2,500 times 1 plus 0.06 divided by 2 to the 2 times 1 power. So this will be 2,500 times 1.03 to the second power, and that will be $2,652.25. So what was it worth to me to compound twice a year instead of once a year? It was worth $2.25, which isn't that much when you're talking about $2,500 for 1 year. When you're talking about $25 million for several years, this makes a huge difference. Okay, and now we're going to look at continuously. My account balance will be equal to my principal times e to the rt power, so 0.06 times 1, so the 0.6 power, and that would be equal to 26.5459. So you can see that $4.59 is the difference between compounding once a year and compounding continuously. So you can predict that quarterly and monthly will be between 26.5225 and 26.5459. So the more frequently you compound, the more money you make. However, what's most significant in terms of the total amount of money you have is what is the interest rate and for how long do you leave it in the account. Okay, so that is section 8.3.